So here we have the integral of x cubed e to the 2x dx. We see we have the product of these two functions of x, so we're going to use integration by parts. We're going to let this first piece be our u and this piece be our dv. So u equals x cubed, so du is going to be 3x squared dx, and dv is e to the 2x dx, so v is going to be e to the 2x, but because of the chain rule we would have generated a factor of 2, so we need a 1/2 here. So applying the formula for integration by parts, we have uv, so that's going to be 1/2 x cubed e to the 2x minus the integral of v. I'm going to write those together because we're going to be looking for a pattern here in a minute. So here's v and du, 3x squared and dx. So now we are going to apply integration by parts again, and we're going to let this piece be our u and this piece be our dv. So u is going to be 3x squared and du is going to be 6x dx. dv here is 1/2 e to the 2x dx, so v must have been an e to the 2x, but we need that 1/2, and there's already a half out there, so that's going to become a 1/4. Now applying the formula, then we still have this 1/2 x cubed e to the 2x out in front, minus, and applies to all of this here, uv, 3x squared times 1/4 e to the 2x minus integral of v, which is 1/4 e to the 2x, and du, which is 6x dx. Now we're going to need to do integration by parts yet again. This time we're going to let this be our u and this be our dv. So if u is 6x, then du is 6 dx. And if dv is 1/4 e to the 2x, then v is going to be 1/8 e to the 2x. This had a dx on it right here. Okay, applying that again, we are going to have 1/2 x cubed e to the 2x minus, so we're going to write it like this, and then times 1/4 e to the 2x, and then we have minus, and we need uv, but actually I say minus, but this minus and minus will make this a plus, and we've got uv, which would be 6x times 1/8 e to the 2x minus the integral of v, 1/8 e to the 2x du, which is 6 dx. And now we actually have this down to something that we can integrate here and finish our problem, and it's going to be 1/2 x cubed e to the 2x minus, here we have 3x squared times 1/4 e to the 2x, and here we have plus 6x times 1/8 e to the 2x, and then we have minus 6 times, if we integrate here, this is going to become 1/16 e to the 2x plus a constant. Now this is our answer. It can be simplified a little bit by combining some of these constants, but the reason I left it like this is because we're going to look for a pattern and come up with an algorithm or sort of a shortcut when we would need to do integration by parts multiple times on problems like this. Okay, so looking at the two functions that we started with, we had an x cubed and we had an e to the 2x, and here is the x cubed, and this piece right here is actually the integration of e to the 2x. If we look right here, we're not going to worry about the signs. We'll look at the signs in a minute, but this is the derivative of x cubed, and this is actually the integration of 1/2 e to the 2x. If we took another derivative of this piece right here, we would get 6x, and if we integrate this piece again, we'd get 1/8 e to the 2x. We did another derivative here, we would get 6. If we integrated here again, we would get this 1/16 e to the 2x. So we can kind of see a pattern of what happens when we apply integration by parts multiple times. We're going to come up with a shortcut. It is called tabular integration because you make a table, and in that table you start with these two functions, and in the first column you put the function that would go to 0 if you differentiated it enough times, so this x cubed. In the second column we're going to put the other function. We are then going to fill out the table by differentiating this function, starting with x cubed and then getting its first derivative, then its second derivative, and then another derivative. And we are actually then going to integrate in the second column for the second function. And one last thing to look at are what the signs did. This first term was positive, the next term was negative, the next term was positive, the next term was negative. So here is our table, and we have first function in this product of two functions, x cubed. If we differentiate it, we get 3x squared. Differentiate it again, 6x, one more time 6, and one last time 0. So this makes the first column of our table. Over here we put our second function, e to the 2x. We integrate again, we integrate again, and we integrate one more time to fill out our table. We saw our signs went plus, minus, plus, minus. They alternated signs. And over here, when we were looking at our solution, we had the x cubed, and that was multiplied by this 1/2 e to the 2x. And so we're going to make an arrow down like so, and we're going to combine these two guys, and then we're going to multiply these two guys, but with a minus sign, then these two guys with a plus sign, these two guys with a minus sign, and we should have our solution. So this is going to be, if we did that integral and we looked at it this way, this is going to be 1/2 x cubed e to the 2x, and then multiplying these, but also multiplying by a minus, minus 3/4 x squared e to the 2x. Multiplying these, multiplying by a plus, we'll get 6/8, which will reduce to 3/4 x e to the 2x. Then if we multiply these two together, but multiply them by a negative, we will have minus 6/16, which will reduce down to 3/8 e to the 2x, and then plus our constant of integration. So here is our solution, and this is an algorithm for applying integration by parts multiple times. It works very nicely when you have the product of two functions, one of which would go to 0 if you differentiate it enough times. We put it in the first column, we differentiate till we get to 0. We come over here and put the second function, we integrate until we've filled out the table. We multiply what's in this first row and column down a row here, and we alternate signs, plus, minus, plus, minus.